In 2001, Olkiluoto in Eurajoki was selected as the final disposal site of spent nuclear fuel produced in Teollisuuden Voima's and Fortum's nuclear power plants. The Posiva company is responsible for the research, development, and planning work related to final disposal and also for the building and operating the facility. Prior to final disposal, spent nuclear fuel has been stored at power plant sites for several decades. During that time, its heat generation and radioactivity have decreased enough to enable technically and financially practical safe final disposal in the deep bedrock. The final disposal tunnels are excavated in the depth of more than 400 meters in the Olkiluoto bedrock, where the conditions are stable and predictable and where the groundwater flow is weak. The fuel will thereby be isolated from living nature, and the changes on the ground surface and in the atmosphere will not influence the underground disposal facility. The animation provides the information about the basis for the long-term safety of the final repository in Olkiluoto. The safety of final disposal is based on the long-term isolation of spent nuclear fuel several hundred meters deep in the bedrock and on several release barriers. The engineered release barriers are the canister, the buffer, the final disposal tunnel backfill and plugs, and the ceiling structures of auxiliary galleries. The bedrock around the final repository is a natural release barrier. Olkiluoto bedrock has been studied since the 1980s by drilling dozens of research holes from the ground surface. The underground research facility Onkalo has also been excavated in Olkiluoto. The investigations have provided knowledge of the Olkiluoto bedrock properties, which have an impact on the safety of final disposal. The disposal tunnels are excavated in bedrock with no major water conducting structures and no fracture zones, which are to be avoided due to rock shear. The properties of bedrock have been characterized and the significant geological structures have been identified with regard to final repository. Safety is also affected by the flow conditions and the chemical composition of groundwater and by rock mechanics properties. The bedrock physically isolates spent fuel from the biosphere and living nature and minimizes the possibility of human intrusion into the final repository. It also provides favorable and predictable conditions for the engineered release barriers. Bedrock also restricts and retards the release of harmful substances from the repository into living nature. The copper canister isolates the fuel assemblies placed inside. This isolation capacity of the canister relies above all on the mechanical durability of the cast iron insert and on the corrosion resistance of the copper overpack. The buffer prevents groundwater from moving in the disposal hole and protects the canister against minor rock movement. The canister, protected by the buffer, remains intact for a long time. The buffer prevents and retards the release of radionuclides in the event of a canister failure. The backfill of the final disposal tunnels creates favorable and predictable conditions for the buffer and the canister. The backfill restricts and retards the release of radionuclides in the event of a canister failure and contributes to the mechanical stability of the bedrock in the vicinity of the final disposal tunnels. The ceiling structures complement the long-term isolation and protection provided by the bedrock. They contribute to the formation of favorable, predictable conditions for other technical release barriers for thousands of years. The disposal tunnels are constructed and backfilled gradually. All tunnels and shafts leading to the final repository are backfilled. Finally, the top part of the tunnels and shafts is filled with boulders, and the disposal site is landscaped and restored to its natural state. After the closure, the groundwater flow rates decrease as the repositories slowly saturate with water seeping from the fracture network in the bedrock. The backfill materials contribute to the restoration of reducing oxygen-free conditions. As the saturation progresses, the groundwater conditions begin to return to its natural state. Spent nuclear fuel increases the temperature of its immediate vicinity with the greatest temperature increases, about 60 degrees Celsius, occurring at the time of the closure of the repository. Gradually, the radioactive attenuates, and consequently, the heat generation of the nuclear waste decreases. Over the thousands of years after the closure, the land uplift in Olkiluoto area will displace the sea shoreline several kilometers to the west, and Olkiluoto turns into part of the inland. Over tens of thousands of years, the northern hemisphere's climate becomes cooler as Earth's orbit and axis angle change, and as less solar radiation is absorbed in the ground surface. As the climate becomes colder, the ground freezes, resulting in permafrost similar to that in northern Siberia and northern Canada today. Permafrost may reach several hundred meters deep. At the permafrost stage, groundwater flows cease. The cooling of the northern hemisphere will ultimately create a continental ice sheet, which will expand over all of Scandinavia. At its largest extent, the ice sheet will be up to about 3 kilometers thick. It is estimated that in the Olkiluoto area, the ice sheet will reach a maximum thickness of about 2.5 kilometers. Ice this thick also depresses the Earth's crust several hundred meters. The design of the disposal system also considers the load caused by an ice sheet of a few kilometers thick. After the glacier stage of thousands of years, the ice sheet will melt, leaving Olkiluoto submerged under a thick water layer. At the edge of the ice, the melting produces a large volume of water, some of which may infiltrate to the final disposal depth through the network of bedrock fractures. The disposal canister and other barrier structures for spent nuclear fuel are designed to perform for tens of thousands of years. However, the safety of the disposal shall not solely rely on the assumption that the engineered barrier system performed flawlessly and in a predictable way. Therefore, unlikely scenarios are also considered when assessing safety. In such scenarios, one or more canisters lose their integrity, or an individual canister is defective from the beginning. In the case presented in the animation, it is assumed that there is a small hole in the lid weld of the copper-iron canister. Groundwater may eventually reach the canister's inner parts through such a hole and cause corrosion. Radioactive substances could first be released into the canister's inner parts and eventually outside the canister. Even though fuel pellet dissolves very slowly, a small part of the radioactive material in spent fuel are in a volatile form that enables radionuclides to migrate outside the canister. Outside the canister, the tight bentonite layer effectively retards the migration of radionuclides. Their radioactivity decreases during the time of the migration. However, some radioactive material may finally reach the bedrock and any possible fracture connected to the groundwater network in the bedrock. However, inside such fractures, the groundwater flow is very weak, so the radioactive substances are retarded in the rock pore network and do not migrate far away from the canister. Low-lying terrain, which is also favorable for surface water formation, is also a natural location where radioactive substances reach the surface. Long-term safety evaluations also cover situations where the flow route of groundwater ends in a household water well. In all scenarios in the safety assessment, individual radiation doses and the exposure of organisms to radiation remain insignificant.